Thanks everyone for being here. I am really excited to present this work. I guess I will start by acknowledging that it's sort of a sad time for many people in the Fed, and I'm just going to take sort of a moment. I don't know actually how we, things change quickly day to day, and I don't know of the people I work with who still has a job and who doesn't. And for those who, I was actually trying to find a group photo of many of the people who work with us, because any of the work that we do is a huge team effort. There's a huge group of people that do field collection. There's a huge group of people that do process studies, experiments to help us learn about the mechanisms of our systems. And really none of this is possible without a huge team of people. So I couldn't find a group photo, but so yeah, here I am to talk about a state-space mass balance model called Ecostate, which I think is a good example for adding bottom-up interactions in stock assessment. And so I gave this talk, a very similar version of this talk at the NOAA stock assessment seminar last week. I asked around a little bit and nobody seemed to complain about the idea of giving it for two different sort of partitioned audiences, but email me if it ended up being bad manners. I don't really know, but it's a different framing I wanted to put here. So basically, like in stock assessment, a lot of times we start with this sort of unit stock. So we think about sort of adult fish and juvenile fish and the relationship between those, in isolation, and without making this too heavy-handed of a metaphor. Thinking in isolation, it only gets you so far, and it certainly doesn't get us as a community too far. There's a different set of models that do these sort of MSVPA, multi-species virtual population analysis, or kind of tactical multi-species statistical captured age models, where people put a predator in here, like this cartoon. I looked at cartoon seal. I would think it's a sea lion because of the way its arms are behaving, but I'm not gonna snipe at the kind of icon that I cribbed. So sometimes people augment these population models with a mortality rate from a predator. They call it, this is a standard. This is basically the way we do tactical multi-species models typically. But what's missing is the bottom-up piece. So things aren't only interacting with their predators. They're in fact also interacting with their prey. And here's a little icon of a copepod. And so, this week we've been subjected to thinking a lot about kind of top-down interactions, and top-down interactions in sort of a population end up having only a certain set of dynamics that can occur and are sometimes bad for the prey. What we need to do is think about bottom-up interactions too, obviously. So we try to do this. We try to think more systematically with these sort of augmented time series models. So here's a representation of what we call a dynamic structural equation model. So it's a state space time series model where you can write out a graph of connections between variables. And so this was one we did in the ecosystem status report in the Bering Sea in 2023. And it basically fits to time series and operates kind of like a more mechanistic form of like a DFA. So it's a smoother on the variables. And if you don't have data on a certain variable, it'll fill it in based on the estimated relationships. And this would, we published this, I don't know, came out last year, but earlier than that. Yeah.
So it was okay to have.
Yeah, please.
Can you remind me why forage fish are bad for collecting foragers?
Well, yeah, no, I can't. I mean, some of these are non-significant, and I'd love to have a whole separate thing about model selection and validation on these. But I think what Ian's getting at is that some of the results here in this initial effort are almost certainly wrong. And so part of what we were interested in doing is trying to think through what happens how do we validate these models? And one idea to do that is to, simulate from a graph and then fit the wrong graph. And that's kind of like a self-test. But really what we want to do is have a more complicated model and simulate dynamics, nonlinear dynamics with known structure, and then fit DSEM to it and see what happens. And so that's actually why I got launched into this path, is to make an operating model to test DSEM. And I was looking through, like Rich Bell did like an Atlantis model, output. All of these ecosystem models I've ever seen generate time series that are totally unrealistic by any standard I've ever, they don't look anything like the data that we actually have in the real world because they don't have processors in it. And so my goal was to make an ecosystem model where I could kind of rapidly tune it and then use it to simulate data. And then I just kind of realized I was having fun. So that was sort of the trajectory I followed here. So the first piece, there's kind of two segments here. The first piece is just sort of the biomass dynamic form, and it's published in Fish and Fisheries. It was done with Casper Christensen, who I currently can't email because he's in Denmark. Karen Aden, Sarah Geitschus, Dave Kimmel, Liz McCuron, Jens Nielsen, Howard Townsend, and Andy Whitehouse. So it's a big cross-program effort. And basically it's using ecopath of Ecostate and trying to adapt it into a state space model that has process errors. And so, to be kind of cheeky, this is sort of my cartoon of the different landscape of models. We've been working in fisheries for 100 years, and we've been coming up with, in stock, we have sort of, you can classify these models in at least two axes that I'm going to pull on. One of them is ecological mechanism. So, if you're a student in fisheries, you might start with a measurement error production model as a class project. All the way over to Atlantis, where they try to put in every possible thing in every possible area and kind of hope that it kind of comes out and gives useful prediction. So there's sort of this ecological mechanism axis. There's also a statistical fidelity axis, fidelity, I mean like the ability for the model to resemble the data that you have in hand, the ability to condition on data and make predictions that condition on the residuals of those data. And so, on the one hand, stock assessment has been taking these sort of measurement error models, like stock census or MSVPA models, and been producing state space versions of them that condition on residual patterns in a way that it's likely to have better prediction. Another thing I'll note is that the stock assessment group on the top left ends up being, if you do a graph of who publishes with who, the multi-species modelers are somewhat bifurcated from the stock assessment modelers. And it's kind of in programs, but also in labs where they train up. And so, there's sort of this state space modeling development on the stock assessment side that hasn't really made the jump into multi-species modeling that I can see, with a few exceptions. There's like Mike Spence has a miser state spacey thing that he's worked on, but for the most part not. And so, my kind of cheeky claim is that, we can kind of start populating these sort of multi-species state space models, and it's a pretty obvious thing to do. And this is sort of an extended argument that it's fairly easy to do. So, Ecostate, it's on CRAN. It's using RTMB, so all of the dynamics are written in R, and then RTMB uses RCPP to just export the stuff you make into C++, and it uses all the TMB machinery to do the marginalization of the likelihood. So you just write out dynamics, and then you kind of basically get a state space model. There's more to it in terms of parameterization and getting it to be efficient, but it's really not terribly hard to pick up. Yeah, so part of this for me has been learning, a lot of the fun of this is just kind of working through Carl Walters's sort of math, so the story starts with Jeff Polovina, who did this ecopath model. And it's basically, at equilibrium, you expect the biomass supply for each pool of biomass, each taxa, to equal the demand for that. So the supply for each biomass pool is the biomass times the production per biomass times the portion of production that's used in the set of species you're modeling, which is called ecotrophic efficiency. And the demand is for each species, it's the sum across all the predators, and and it's the sum of, for each predator, the predator biomass times the diet proportion, the proportion of its consumption from each prey, times the consumption per biomass. So this is like a pretty intuitive, you know, supply demand claim. So, you know, you can write it out in linear algebra, you know, so you get these Hadamard products on the left, and then this kind of Hadamard matrix product on the right. And you just, you know, typically the simplest way to do this is just kind of plug in biomass and P and W, and then you know, just solve for and D, assume D is known, just solve for ecotrophic efficiency. In reality, you know, people end up you know, you can pick 3 of the 4 and then calculate the 4th from it. That standard kind of ecopath land kind of process. And then once you've done that, you can calculate equilibrium consumption and use that to compute tracers like trophic level or pelagic production or other, you know, stable isotopes. So that's the Polyvena part. The next part is this Ecosim, which is like the kind of where I think Carl Walters kind of came in. And he recast this equilibrium as a differential equation around the equilibrium. You know, so this dBdt at equilibrium will be 0, but away from the equilibrium, you get this differential equation where there's a growth rate minus a natural mortality rate, which are per biomass rate values, and that times the biomass. You know, so it's this linear ODE. There's an ODE that you have to be solving. And you can do this and this is why RTMD was nice for me. I don't typically do these like state-space ODE models, and so it would have been annoying to try to build an ODE solver in TMB or God forbid ADMB. But instead I can just use R code to do these kind of solvers that I've thought about for 20 years. Yeah, and so the dynamics of this, the G and the M, which are the important parts here, are going to be driven by consumption equations. So here we have this consumption that, you know, the consumption at a given time is equal to the equilibrium times a modifier for the predator functional response times a multiplier for the prey functional response. And here I'm stripping it down to like the simplest form. You know, I'm not putting in handling and foraging time adjustments. I'm not putting in a prey functional response. The middle term is the predator functional response. This is sort of the and here I'm putting in this sort of foraging arena form of it. It's, you know, you can derive this from foraging arena stuff. It's sort of a type 2 functional response given the vulnerability parameter. And so,
clarifying, so CS2, S1, that's consumption of which direction is that?
yeah, so I'm worried I'm gonna get this. Yeah, I think that the S1 is the predator and S2 is the prey, but I might be wrong. And I haven't updated this. Now I use I and J for predator, prey and predator. So yeah, to get the indexing right, we should really talk later. But so given this consumption equation, you know, given any kind of non-equilibrium biomass, you can solve for the instantaneous consumption, given the vulnerabilities, and then you can plug that consumption into these expressions to get the G and the M that's then actually used in that differential equation. So, so given a biomass, solve for consumption, you then convert that to growth and mortality rates. It actually differs between primary producers, heterotrophs, or a detritus pool, which I'm not showing here. I stripped that out. So there's sort of some extra stuff related to, you know, those 3 different types. And it was incredibly annoying trying to work that math out. And then the mortality, you know, there's a predation part, like an M2 part, and then there's an M0 part. If this is a stock assessment model, or, you know, or an MSVPA, there's sort of a part, there's a residual natural mortality rate, which is derived from ecotrophic efficiency. So ecotrophic efficiency is how many of the predators are being modeled. If you have no predators, ecotrophic efficiency is 0. And so the residual mortality rate is P. And at equilibrium, the production per biomass is being matched by mortality. So it kind of makes sense intuitively. There's no predators. All of your mortality, that first term is 0. The second term is equal to P, which is the kind of balance rate here. As you have more predators, included, E will go to 1, residual mortality drops out, and you're tracking all of the, all of the mortality via consumption. Yeah, so next we take this and we augment it with process errors. And so we're going to make these sort of annual process error deviates that I'll call epsilon, which are deviates in a rate. And I'm also going to put in a fishing mortality rate. So instead of putting in like the Baronoff-Catch equation or Pope's approximation, like you do if you learn stocks, I'll say none of this stuff is stuff that I've seen written out in Carl Walter's stuff because he just thinks it's too complicated to explain to people, I guess. And it's not in Quinn Dorizo. And so like people that take a pop dye class, I don't know anybody who actually goes through these equations. So partly I'm just trying to, the paper is about trying to explain these equations. I think any of us could code it up. We just have never really been encouraged or given an opportunity to do it. So anyway, here I've got a fishing mortality parameter that I'm going to estimate as a vector of parameters. It's like an explicit F parameterization. And then I'm gonna keep track of this eta. I think that's an eta on the bottom, which is going to be the accumulator of fishing mortality times biomass integrated over time. That's just going to be an annual cash integrator. So the sum of biomass plus eta, d biomass dt and d eta dt is going to be the g minus n plus epsilon. So F is just coming in and portioning out some of it into this cash pool, which I'll compare with harvest at the end of the year. Epsilon is this processor term. I run it, I do this integral across time using an ODE solver. I sum up the catch in a given year and compare that with harvest, and I assign that a low CV. So it's this is the explicit F thing in a model, kind of force it to fit catch. The abundance index is, I'm doing it at the midpoint of the year. I mean, there's a bunch of ways you could do this, in terms of sequencing within a year, and I'm not really going to get into that because I don't care. But and then the process error has this sort of normal deviation. So, you spend some time matching this up against RPath and getting the detritus pool to work, despite the fact that nobody writes it out. And you eventually get, something that works. So here's a simulation with just a vulnerability of 2 for each species. It's just this sort of made up 6 species thing where I've got a pelagic production. I've got a benthic detritus pool. I've got 2 mid-level consumers that are like, mixed between pelagic and demersal pools. And then I've got top predators that are more mixotroph. The demersal is sort of slower life history, which is sort of the theory plane. And so if you balance it out, you get detritus is 10, producer biomass is 0.1. You can kind of follow through how the balance is being achieved here. If anybody's interested, and you can track all the rates and so forth. And then if you subject it to fishing, so in this case, I'm just showing a simulation with process errors where I fish the top 2 predators at a rate that's increasing over time and doing it with, stochastic draws from the simulation. And so the predators on the bottom are going down in biomass on the right. The growth rate is going up because they have, compensatory growth rates. They're compensatory growth rates. That given the vulnerabilities, the mid-level is actually about constant over time, and all of that impact immediately goes down to the biomass. So there's this trophic cascade that's being created here with the biomass that the producer and the detritus are going down. Anyway, so depending on the vulnerability parameters, you get different density-dependent relationships. You can do this if you do a simulation of this. You simulate data from the model. I'm just doing 40-year simulations. I'm doing biomass in every year, freely estimating the equilibrium biomass, but I'm assuming I know diet and production for biomass, consumption for biomass. If you turn off process errors, so just strip this back down to like a measurement error model, you get the errors for growth or mortality or biomass in this kind of blue area, and if you run it as a state space model, you get the red, so the obvious point being that, unsurprisingly, if you run a state space model, you get better estimates of biomass because it's conditioning on the pattern, residual patterns you've seen recently. But when you improve the prediction of biomass, you also improve the prediction of their growth rate and mortality rates. You get better inference about demography that you're not directly observing if you're able to condition on kind of misfits, basically. So one argument I've had with and I've said this to people, a lot, is that, we have these sort of multi-species models where, they systematically misfit for one decade, they're over predicting for one decade of a predator, and then they underfit for the next decade, and they kind of hit right on average. But when they kind of are systematically missing for a decade, it means not just that they're wrong, but that their predicted consumption is wrong. And so that error is propagated all through your ecosystem model when you have a measurement model. If you have a state space model, you can get those, you can get right, not just on average, but for individual years, and propagate consumption trophic interactions through correctly. Okay, so the Bering Sea ecosystem model, this is a stripping it back from the RPath model that Andy Whitehouse has. So taking like 75 taxa and compressing it down to 11. A lot of it's going into this benthic category I. But in the top up there is northern fur seal. I don't think I show this in a super useful way, but there's northern fur seal that's eating pollock. And then there's arrowtooth. So like probably B is arrowtooth, and I don't know, maybe B is, anyway, I should just make shit up here, but there's a bunch of stuff going on. It's fitting to, the design-based biomass index for 3 species, copepod, pelagic zooplankton index from Dave Kimmel, a primary production index from Jens, krill index from our summer acoustics, the northern fur seal from the fur seal people, total catches, etc. And I actually also turned on the P parameter, W parameter with tight priors. So there's sort of a Bayesian prior thing happening here too. Yeah.
So that's all listed as indices. Where's the absolute scale information coming from?
So
Taking something to like the design-based estimators.
yeah, well, exactly. So the cod and arrowtooth, I'm assuming Q equals 1. Pollock, I think I freely estimated Q. In the later example for the Goa, I used the same Q prior for adult pollock that Cole used. So I'm kind of scrounging around trying to, you're right that if I open up Q and equilibrium biomass for everything, the model doesn't. Maybe once I have age structure in for every species, I can read off the fishery as depletion experiment. Maybe I get lucky, but I don't think it's probably that likely to happen. And so the point being that I agree that there's a bunch of like data weighting scale estimation issues here that I really have not cracked open. Okay, so here's the fit to the catch data. So I'm doing this explicit F thing. So it's conditioning on catch the way you expect. Here's the estimate of parameters. So I've got Q estimated for pollock, copepods, chlorophyll, others will think krill. I've got equilibrium biomass estimated for cod, arrowtooth, and northern fur seal. I've got process error, the log standard deviation of process errors for pollock, cod, arrowtooth, copepod, and northern fur seal. Trying on process errors for those. And then I've got the ratio, the delta is the ratio of initial to equilibrium biomass. So kind of that in stocks is like an equilibrium agreement parameter. Yeah, I'm kind of fixing the scale as Ian pointed out for species where I can make a case that I've got a good absolute index. Yeah. And then in terms of in terms of fits, here's sort of the fits the data. So X's are the kind of initial, the unscaled value of the index, and then the dots are the catchability scaled estimates. So biomass for pollock, the catchability is less than 1 from the bottom trawlet, so it's ends up estimating higher than the nominal index. It's not really fitting corpopods at all, but it's hitting a bunch of the stuff like chlorophyll, northern fur seal, and so forth. So, and doing this kind of ramp up of arrowtooth from the 80s to the mid-90s. And so, so that's just kind of a time series model, but then the model's actually using that to compute these sort of derived time varying growth and mortality rates. So it's basically a big machine for doing a state space time series model, but trying to parse time varying productivity parameters based on interactions. So, so pollock, there's a growth rate. The red plus the blue, the green minus the blue minus the red is going to be the dBdt. It's going to be the average growth term. So pollock actually has these cases, even with no fishing mortality, the model thinks it has declining negative productivity during some of the warm period. During some of the years. That cod has fluctuations with stanzas too. I don't know. I don't have that much to say about it.
Jim, I'm still trying to wrap my head around the model. I've never really worked with these. What, just as if we could entertain a thought experiment, what happens if you put species in here that aren't actually interacting at all? How does the model turn off, like what does it look like when it turns off interactions?
Yeah, I mean, that'd just be there's the diet matrix. If that diet matrix is with no interaction, with only self interactions, I guess every heterotroph would just be a diagonal matrix where they're cannibalizing or something, I guess. I don't know. I do actually have a vignette where I make a production model. But I have to think about how I do that. I don't think you really can turn off interactions.
Well, I mean, so if you go back to the fits, so like why? Or I guess maybe if I put it a different way, like what if your diet matrix is like biased or something? I'm just trying to think through like how the model would propagate that through, like what would go wrong and what would that look like?
Yeah, I mean, some of it's getting slopped up in this ecotrophic efficiency thing, so like if you've got an absolute index for the predator and the prey pair both, but you think that predator is eating a higher proportion of that prey than it really is, then it's going to need some way of making that prey. It's going to need some way of making sense of that. So in that case, it ended up with a negative ecotrophic efficiency, which is why it's nice to put priors on those parameters. So like the way I've got it coded up, you can have, P and B and E and W all as parameters and then bound them. I haven't really played. I mean, the honest answer is I don't really know what I'm doing with this class of models, but I don't actually know that because people don't fit them. Everybody spends like 3 years tuning their own model, and then nobody really looks at, if they're lucky, somebody else in their lab will also look at it. But my feeling is that there's a lot to learn about this class of model is the point, and we can do that once we can fit up like a stats model and actually hand it around and look at each other's work a bit.
And so, yeah, thanks, that's helpful. And so what's happening with like other, like why would you, is that just because?
Oh, well, I just put in the units all really shitty. I mean, I'm just estimating a catchability coefficient. I probably should have made these log scale axes or something because the black line, I can't even tell if it's doing anything. It's all swamped by the X's because that's just a made up unit.
Well, yeah, so say that part again. So I would look at that and say like cube's crazy, which means that
but it's not an absolute index. It's just taken from a not area swept survey. So there's just a missing proportionality constant. That
right, okay.
Yeah.
If you centered all those things.
It would have been a better plot. Yeah, I'm sorry. Yeah.
Okay.
Here's the process errors, so pollock has these sort of, 30 to 40% differences in actual biomass relative to predicted, process measurement error model only dynamics. Northern fur seal has this kind of positive production, then negative over time. Arrowtooth is actually pretty white noisy. But, process errors are substantial. And if you cut out the process errors, you lose a lot of what's actually happening in the data. So here's what happens if you get the catch but turn off process. Black is the full model. Blue is if you do the same model, but you turn off process errors and refit it. So pollock basically suddenly goes from the pollock that we kind of generally agree on is what's happened to basically a flat line. Like a lot of the dynamics of pollock are not being captured in this model. It'd be in a processor only trophic model. Cod, I would say it's capturing a little bit of the cycles from trophic dynamics, but not much. Arrowtooth, the big story, the model is just saying it started out of equilibrium. And so, with or without processors, you get this sort of increase over time. Yeah, so not to belabor the point, but you really lose most of the dynamics for, the kind of stanza dynamics is not a trophic thing. It's some kind of bottom up, it's the physics thing. So if you want to understand that in stanzas, or you care about stanzas, which everybody does who studies the Bering Sea, you need a processor model, or you need some other.
Stanzas to define standards.
Like I'm sorry. So like the cycle of warm and cold, the first warm stanza was like in the early 2000s, and then there's a cold stanza again, right as we did Berserk. And then there's another warm stanza.
Jim?
Yeah.
So just there's like a full ecopath model for Bering Sea would produce this flat line for polar. Is that what they do?
Yeah. So I again, and I don't mean to throw stones here. I don't claim that I just want to have a model that actually captures annual variation. And I think that will do better at producing stuff that I want. But yeah, part of my hope is just because it's an R package, we can play around with it more.
And purple here is just the same model, just only with the 4.
Exactly. So that's like the mice style model. Exactly. So you get similar dynamics, but because there's less predators and pollock, it's sort of dropping the biomass down. We could go into that, but it's just the way I'm doing bounding trophic efficiency is causing it to drop the scale a bit.
So as you strip away species in your food web, essentially the process error is just trying to absorb that effect.
Well, I think that the way I did the scale on pollock is that I said that it had ecotrophic efficiency of close to 1. I'm trying to remember this now. And so as I got rid of arrowtooth and northern fur seal and cod, there's fewer predators and the same ecotrophic efficiency. And so it's accounting for that by just dropping the scale. So it's getting some scale from an assumption about for pollock. That's using that to estimate catchability for that stuff. So I'm not saying that's the way everybody should do this. It was just sort of a first pass at how we can use this as a stats model. You also, because one of the reasons it's a nice model is that the growth and the mortality are this additive. You can do an additive decomposition. Both of them are just the sum across predator prey. And so this stacked histogram, stacked bar plot is the growth and the mortality time series we saw earlier, but now it's partitioned into individual predator and prey interactions.
Growth in this formulation is both somatic growth and recurrent.
Yeah,
and the way we used to think about growth.
Well, so assuming I get to it, I've got a whole second part that's about the 8 structured piece. So maybe I'll just plow forward here, but we don't have many predators modeled for cod, so it's mainly the M0. Pollock, I would say most of the variation in modeled growth is due to variation in krill. And I don't know that I have it in here, but well, anyway, yeah. I did a run without the zooplankton time series, and it affects things, obviously. So, so basically the PSA is you could download the package. This is a vignette. You just say the years, you say the taxa, you say the type, the diet matrix, PB, QB. U is the unassimilated food, just the stuff they eat and then spit out or whatever, vulnerability matrix, but it's defining parameters. To simulate data, you make a dummy matrix of biomass and catch and just plug it into this tidy model kind of style R function. You can modify the parameters, plug it into a function called the simulator, and simulate data. And then you can fit it with sort of similar lines, so this is sort of code that is, I think, fairly straightforward for people. I mean, there's a lot of arguments because the model has a lot, but relative to like stock synthesis, it's way simpler, in terms of interface. I would say it's kind of in complexity a little bit like WHAM, it doesn't have as many arguments related to fishery selectivity or whatever. Has more, parameters maybe that people aren't used to, but I don't think it'd be hard software for people to pick up. Yeah, so we can decompose population growth rate by prey. You can decompose mortality rate by predator, and you can capture population cycles using process errors and see that in simulation land improves things and also is necessary to capture patterns that we observe. The next piece, which is in review at Fish and Fisheries and is on archive, and I just didn't update the slide, is sort of about like skinny pollock versus fat pollock. So, and I forget if I tried to get photos from UCOL or not. I think anyway. But yeah, like for a lot of species, what's driving dynamics is not necessarily recruitment, but it's kind of variation growth. Cole and I have a paper looking at this from 10 years ago where, if you've got sort of a based on fish life, you have like a simulator of different life histories, and if you do these perturbation experiments on adult mortality or juvenile mortality or L infinity or K for different life histories, it'll change your fishing mortality and biomass reference points. So this shouldn't be too surprising. One takeaway from the paper was that mortality rate has a huge effect on reference points, equilibrium reference points. So things that affect mortality rate is important. But, really the growth rates also are having these very large impacts too. So, we don't want to just only do this MSVPA style thing where we're correcting for mortality rates. We also need to think about interactions in growth. And so where we want to get to is this is sort of the end point of this development, is that on the top, you can have this no fishing scenario over 70 years from 1970 to 2040, where you've got biomass of adult pollock and juvenile pollock. So it's ages 0 to 2 and then 2 to 15 plus or whatever it is. And so, without fishing, it's at equilibrium. And so every year is shown on top of each other. You've got this sort of abundance at age declining quickly for juveniles. There's a constant mortality rate for juveniles, and that switches at that stanza break at age 2. And then there's a plus group here where it kind of dog legs up because you've got this accumulator age. And the weighted age is also constant over time. So, we got the equilibrium stuff right. You started out, you run at equilibrium, nothing's changing. That's it. But if you run it with increasing fishing mortality on adults, the adult biomass is going down, the juvenile biomass is actually going up a little bit. So if you just have a standard Beverton-Holt relationship, you wouldn't ever see that in a stock assessment model. I mean, that would look like Ricker, but what's happening is they're actually growing faster. As you fish down the adults, their prey is becoming more abundant, and then the juveniles also have some overlapping diet with the adults, and so the juveniles are not just surviving better, but they're also growing faster. So the age structure, as you go to 2040, the mortality rate for juveniles is a little more shallow. You can slightly see the adult rate is much steeper because they're being fished. And then if you look at weighted age, as you go from their red, early to late, their weighted age curve is going up a bit. So there's a sort of compensatory individual growth rate that's being built in via this sort of density dependence chart.
So there is no.
No, there is, so, I'm putting in the way I'm cooking it is like, I'm putting in the same functional response that, the vulnerability does, which is a beverage control. And so, and I haven't actually seen this, but like, because it's beverage control, I can back out vulnerability from steepness, so you can do a prior on steepness and plug it in to.
Are they both starting at the same point in 1970?
Yeah. Yeah,
Because the abundance scale is very different, right?
I think it's just the ticks. I don't know why the ticks are.
Are you missing the 20 on the top?
Yeah, but I'm not, yeah, the abundance, I think that it's the same, but I think it's just, yeah, I think because the bottom is different, it's rearranged the ticks, but I'm not 100% sure on that. That's what I think. Okay, yeah, so what I guess that the theory here, which is like, again, like what I feel like we should have been taught in some textbook at some point, is like, everybody uses this von Bertalanffy length at age relationship, and this is like the first thing you learn in a fisheries class. But nobody actually goes back and revisits the von Bertalanffy, the theory of where that growth curve comes from. So the top is this sort of von Bertalanffy function where dWdt, the growth rate of an animal, has this anabolism or gain term and a catabolism or a loss term. And there's a D parameter, which is typically 2/3. It's like, based on volume to surface area consideration. But if you freely estimate it, it's the generalized von Bertalanffy. H is a anabolism rate, and K is if D is 2/3 and you have isometric length to weight, collapses to the standard von Bertalanffy, where that K in weight is 3 times the K in length or something like that. I'm gonna get, it's either 3 times or 1/3. But anyway, so this is sort of where this comes from. And so people use this length relationship without necessarily thinking about the fact that they can they can derive that as an outcome of modeling consumption, which is the anabolism term. And so if an animal is starving, if there's no food, that anabolism term is 0, and so the model predicts that they'll have this asymptotic decrease in weight as they starve. If consumption's at biomass, and then you expect it to be at the equilibrium. If consumption's per biomass at equilibrium, you expect to have the equilibrium length at age. And then if you double consumption per biomass, you'd expect it to double anabolism. And so this set of set of expressions allows you to calculate individual growth rate as an ODE for any consumption value. And so there's a little bit of there's some bookkeeping here, which is sort of basically because you're going to replace an ODE with a difference equation, you're going to want to discretize within year. And so as soon as you do that, you've got to do this sort of how total consumption is being parsed into each of those discrete bins. And so that gives rise to this alpha term. So you discretize this equation into subintervals, and at equilibrium, the equilibrium anabolism will equal equilibrium consumption per biomass when average, summing across discrete categories and across ages within a stanza with this proportionality constant alpha. So there's this sort of alpha term that's bookkeeping term. And then you can just use that and plug it in. You change consumption, for a given non-equilibrium consumption and a non-equilibrium age structure, you can calculate the consumption per biomass and scale that with alpha to get this sort of non-equilibrium individual growth. So this is sort of what's doing the work of this mechanistic bottom-up growth model.
Can you repeat what stanzas in this?
Yeah, I'm sorry, I'm kind of trying to speed up a little bit, but, the stanza is this sort of. Basically, EWE couples this sort of age structured dynamics into a biomass dynamic model. Where all of the rate parameters come out the same. And so, it does that by treating a group of ages as a biomass pool in the biomass dynamics. And it calls each of those groups of ages a stanza. So you could say you have an age structured population, but it's gonna be doing the ODE for biomass in
It's a groups.
yeah, it's like yeah, exactly. So in this case, I'm doing two stanzas like juveniles and adults.
Gotcha.
And it has to be doing the math of the age dynamics such that it matches the math of the biomass dynamic part.
Thanks.
So anyway, you know, there's some math, it's on GitHub. But that's sort of the high level conceptual piece, is that sort of link that I've never seen anybody actually write up in a stock assessment book. Which is that von Bertalanffy growth comes from a consumption equation that is actually fairly straightforward to calculate. So I can fit this to catch time series abundance, age composition, and potentially weighted age, estimated catchability coefficient, steepness, survey selectivity, natural mortality rate, growth parameters, and predator prey vulnerability. And the big limitations are that you have to fix the fishery selectivity to be constant within a stanza. I mean, maybe I can relax this, but I haven't bothered thinking about it. And there's a lot of interesting research somebody could do here. And then I'm also fixing age and maturity because I'm not like fitting a maturity ogive or something. So the demo that's in review is doing this for the Gulf of Alaska. We've got a age structure for sablefish and pollock, and then biomass pools for, you know, a bunch of other stuff. We've got catches for the adults of those two species, biomass indices for adult sablefish pollock, large composite phausids, and then age comp data for sablefish and pollock. And my claim is that we want to, you know, we want to be able to view this as a assessment model. So I want to get reference points and age in tracking cohorts out of it. I want to see, is this model do better at predicting weighted age? You know, is it useful at predicting changes in weighted age? And can we do short-term forecasting? So, you know, here's the kind of same biomass dynamic stuff for the Gulf of Alaska, where we get this sort of sablefish is adult sablefish is B and F is adult pollock. Again, there's sort of this pelagic producers versus demersal detritus base of the food web. You know, trying to line up biomass for sablefish and pollock for juveniles and adults. I mean, my pollock is coming in a little low relative to the assessment. Whereas mortality rates coming in a little high for pollock, a little low for sablefish, et cetera, but well, I think the sablefish assessment starts at age 2. Or no, pollock starts at age 2. And no,
So
sablefish starts at page 2. Yeah. And yeah, there is no juvenile sablefish in the assessment. If we look at age comps, we can track cohorts, you know, as expected. I put in this little Dirichlet multinomial thing, you know, with an input sample size, but the Dirichlet part was it was collapsing the multinomial. It wasn't downrating at all. So I just went back to multinomial. And so like, you know, it captures like this big cohort in 2012, you know, aging through, you know, you can track cohorts for sablefish, but it's harder because they live annoyingly long. They're almost as bad as a rockfish, but yeah. And so if you look at, you know, and then I'm not fitting weighted age data at all in the model. So I decided the easiest way to do this was to leave out weighted age and use it as a purely out of sample evaluation. So The predicted weighted age is shown here, where there's this sort of peak in sablefish and a peak, a low to high to low, and then a recovery for pollock. Whereas the observed is shown in the bottom. And so, by eye, without arguing about correlation coefficients, I would say that the pollock, like the observed, starts low, increases, it kind of hits the time of increase off, is off. And it also erroneously thinks there's going to be this weighted age bump as they sort of start cannibalizing a big cohort recently. But the correlation is generally decent for pollock. If you cut out the forage index data, the biomass indices for forage species, it just looks worse because it doesn't really capture the sort of remaining high in the mid 2010 time.
What are each line here?
Sorry, so it's the weighted age for each age in the model. So for sablefish, there should be 30 lines, and for pollock, there should be 10 or something. So, the takeaway, if you have no forage biomass indices, it's just predicting fluctuations in forage biomass based purely off density dependent, like a kind of biomass dynamic density dependent response of the forage. Whereas if you put in forage data, you turn on processors and have it actually fit the biomass data, and then that improves its ability to predict weighted age variation for pollock. Yeah.
So where does it get information about the absolute weight in age? Is that because in teachability?
Well, okay, so there's all these details. So the way that Carl did it originally is all relative to all of the weighted age is relative to equilibrium asymptotic weighted age. So it's all 0 to 1 scaled. I actually did a thing where I turned on estimating. If you put in weighted age, obviously you can estimate that, K and W infinity. And so I did that and confirmed that it didn't affect anything. Then I left it at this form, so it's easier to compare with FARPath.
Do you have any thoughts on why sablefish is just not, that's a totally different pattern in
No.
data?
I don't know.
It's interesting because Matt Chang just published a paper on density dependent growth for sablefish, and I'm not seeing it in the raw data there.
I know.
It looks like it's just weighted age is just going up for the older fish and down for the younger fish.
I don't know that I want to comment on that latter question, but yeah, I don't find any strong evidence for density dependence in weighted age. And then you can run it on future years with no data and whatever catch, in this case I'm just conditioning on observed later catch and doing these kind of retrospective peels. So this is sort of a visualization of like Mohn's row, basically. And so, as you strip data away, you get these sort of biomass, as you strip data away, if you've got data through 2023 and you're predicting 2023, you've got pretty good at intervals. As you strip data away and go through the colors and go through the left in each one, the confidence intervals get broader. But generally, the predictive intervals include, the full data value in many cases, except when they're kind of missing a big recruitment peak, like for pollock, the model predicts a big one in 2020. And there's sort of a whole question about why it disagrees a bit with the assessment model, but. So, and then this is the biomass.
I'm sorry, we have one question online from Matt Chang. Hey, Jim, curious if you looked at cross correlations with lags, but also correlations with just the well sampled ages.
Yeah, so Matt, is a co-author on the paper, and thanks, Matt, for all that for all your help on it. And Matt helped me do a run both for sablefish and for pollock, running the raw weighted age through the triple separable thing as a smoother, just to see if sample measurement error was causing the correlation not to look as good, and that didn't really fix the lack of correlation. And then cross lags. I didn't really go down all the stuff, the kind of like time series weighted age stuff that Matt, I'd love to follow up with you about, like the triple separable cohort tracking kind of stuff. this is like very much the mechanistic far side of how to do weighted age, whereas I operationally actually think that it's probably better to do the GMRS stuff, but the time series stuff, but yeah, so you know, we can model top down and bottom up interactions. I hope for all of our sake that we remember about bottom up interactions. The forage biomass can improve predictions of fish growth. And we can link, yeah, individual growth to population consumption. So there's this sort of missing ecology about consumption driving the Mont-Bertalanffy growth function that Carl obviously knew and built in EWE, but he did it in a way that's so complicated that nobody in my pop-dye circles ever really picked up on it and took it and ran with it in a different context. So, you know, somebody should, so I'll caveat that and actually say that Kimberly, you know, working with Jim Bentz, like, has a paper doing some of this weighted age stuff, and I still don't know the details because I haven't looked into it too much. So some of that kind of Great Lakes, Wisconsin model community, I think also does know this stuff, but I just haven't really seen it in Gadget. You know, the mice models I've looked at, or, you know, it's just not, I wouldn't say it's widely done. So it's something I'd love to see more and to work with people to do. In terms of future direction, so Maurice Goodman is helping, you know, actually there's a dev branch of Ecostate where the DSEM is merged in. If I have time, I'd love, you know, and I still have, you know, if I have time and other caveats, I will be interested in doing fitting to consumption data. And there's a huge need for more kind of road testing, both for MSE use, you know, for kind of performance testing use, like figuring out where it's getting scale information, like Ian asked, you know, so there's a bunch of collaborations I'd love to do on this stuff if anybody's interested. So with that, you know, thanks to co-authors and also, you know, obviously the various sort of constituencies who, you know, we get up every day and try to help by working on it. Yeah, that's it.
Right, any additional questions? We've got a minute or so.
Well played.
Yeah.
May I ask all mine during the talk?
You mentioned on the last slide, STEM content data. What other kinds of data would be helpful? If you mentioned keeping weighted age out as a, what else, what other data would be good to check out?
Yeah, I mean, I'd love to think this stuff through more. You know, those are the ones I've been thinking about. I mean, obviously, like, it'd be great to down the road, see if anybody cares about length at age, you know, and but yeah, I don't know. Yeah, there's sort of like a question about whether this is just like a research model or whether there's actually enough interest that we try to do operational stuff, you know, like actually update the code to make something that we all can share. And so it sort of depends on community interest, I guess, whether I invest time and continue to try to make the code better and more general, or whether I just call it like a demo and hope other people run with it.
You've got copepods and one other prey here. What other indices do we have to feed this thing?
Yeah.
It strikes me there's a lot of prey out there, and most of it we don't sample well with trawl surveys or anything else.
Yeah. Yeah, I don't know. No, that's a good question. You know, a lot of this stuff, same with DSEM. I mean, a lot of it's like trying to you know, and I do think there's evidence of cases where having that lower trophic data can help with things that we want to do for management. But I'm with people at USGS, so Mark Henderson and Joe Lengen and Chris Cahill and Suresh Sethi, we're putting in a Great Lakes proposal where lake systems, you know, typically have more information, they say, on lower trophic and less on the fishing part, you know, because real surveys are expensive. And so I think that's why the lake people, Carpenter and Kitchell and folk, you know, do have more of a history of bottom up and more kind of lower trophic stuff. So it'd be fun to do this on some of the fresh inland stuff where we have better lower trophic information.
Sweet. Any other questions online or in person?
How easy would it be to add in temperature somewhere there as like,
Yeah,
like growth rate or like linked to metabolism in the.
did we talk about this?
No, maybe in an email somewhere.
Okay, that's another one that so basically the original von Bertalanffy talks about doing H and K both as a allometric temperature. And in fact, you know, the temperature size rule that everybody's talking about, kind of trendy, has it that K, how does that work? That H is more affected by temperature. So like if they're both positive, but H is more positive with temperature, then you get a faster growth. As temperature increases, you get faster juvenile and lower adult growth. And so, you know, yeah, so exactly. So that's, you know, that's what von Bertalanffy published in the 20s, you know, 100 years ago. It's like, so yeah, I think it'd be a fun platform for doing this temperature bioenergetic.
Would it be thinking like part of that is dependent on prey availability? So is the model set up the way the linkages are that like you could also have temperature be impacting some of the availability that goes into when you show that next slide about.
Well, so I think Maurice is hoping to think more about this, and you know, so he's putting the DSEM in stuff to do the DSEM stuff in to do this like temperature effects, predatory overlap effects, process errors. I don't know. Yeah, like if you are doing a postdoc with somebody who's interested in temperature, it'd be super fun to, but yeah. Yeah. I'm sorry to speculate about next week, but yeah.
Okay, sweet. Well, thank you, Jim, so much for that.
Yeah, thank you.
And thank you, everybody, for coming to QuantSem today. Next week, we'll hear from a fellow Perm student, Zoe Rand, on their talk on Bayesian models reveal endangered Antarctic blue whale population is increasing, but still far from pre-whaling levels. So with that, yeah, happy Valentine's Day, everybody.
Thanks.